We present our work on continual adaptation of semantic segmentation using complementary 2D, 3D data representations. Let us first have a look at how neural networks are deployed in a classical supervised learning paradigm. First, you have to collect the data with your robot. Then you have to label the data for your desired task, in our case semantic segmentation. Then you have to train the network on a generated dataset, which nowadays often requires large computational resources. And finally, we can deploy the network on the new data experienced by the robot during its mission. And suddenly something goes wrong. This requires to repeat this process, which is costly, time-intensive, and prone to errors. Our work tackles the challenge of distribution mismatch between the available training dataset and data encountered by the robot during its mission. Today, most neural networks deployed on robotic systems are trained once and kept fixed during deployment. This prohibits adaptation of the robot to its operating environment. We tackle this problem for semantic segmentation, where the data distribution depends on the robot's environment. Ambiguities and missing context make this an especially hard problem. In our system, we aim to adapt the segmentation network during the mission. To adapt the network, we use 3D mapping to create accurate pseudolabels from multiple observations, therefore creating a supervision signal in a self-supervised manner. Let's have a look at the pipeline's details. A robot perceives its environment using an RGB-D sensor. An initial semantic segmentation is predicted from the captured 2D images. Precise camera poses are estimated using an RGB-D SLAM system. Individual 2D semantic segmentations are accumulated in a 3D volumetric map. We can now ray trace the map to generate pseudolabels. An experience replay continual learning strategy is used to update the parameters of the neural network. The continual learning strategy trades off preserving previously learned and adaptation to the current environment. The illustrated video shows the color-coded semantic segmentation predictions of the pre-trained neural network. Common failure modes include disagreeing semantic segmentations over consecutive frames for the same objects. To mitigate this failure mode, we perform 3D voxel-based semantic mapping, which enforces multi-view consistency. Individual predictions are fused into the map in a probabilistic manner. After ray tracing, the generated pseudolabels in the bottom row apply to the multi-view consistency constraint, but include artifacts induced by voxelization. Here we illustrate the direct comparison between the pre-trained and adapted network predictions. We show that the adapted network outperforms the pre-trained network in average by 9.9%. Let's have a look at some numerical results. We perform experiments on 5 scenes within the ScanNet dataset. One pret refers to the performance achieved by the pre-trained semantic segmentation network, averaging an accuracy of 51.5%. The pseudolabel generation process increases the accuracy in average of 3.4% compared to the pre-trained neural network. When we then adapt our network using the continual learning strategy with the generated pseudolabels, we achieve a performance of 56.6%. We hypothesize that the performance increase can be achieved through the fact that the samples provided in the memory buffer regularize the adaptation of the network, which then learns to filter the artifacts induced by voxelization. We compare our method to a state-of-the-art domain adaptation strategy and simple fine-tuning on the generated pseudolabels, and we achieve superior performance compared to both methods. Additionally, we illustrate the multi-view consistency by measuring for each voxel the amount of disagreeing predictions. Here, yellow refers to high agreement of all predictions for a specific voxel, while purple indicates multiple disagreeing predictions. After adaptation, the scene is clearly more multi-view consistent. Further experiments are provided for scenes recorded in-house using a handheld RGB-D sensor. We are among the first to show the effectiveness of continual learning for semantic segmentation for a real-world robotic use case. Thanks a lot for your attention and enjoy the conference.